Hello, in this video we'll talk about differential information and differential entropy. Um, we know that for a probability density function f of x, we define minus logarithm of the PDF as differential information. So if you have a PDF in a logarithmic scale or in a minus logarithmic scale of the PDF is called differential information. Now, if you average information, we call it entropy. So expected value of logarithm of PDF with a minus sign is called entropy. It has some physical significance in physics, thermodynamic, physical, quantum, mechanical, quantum, and so on. So in this video, we present Kullback-Leibler divergence, which proves that the entropy of a distribution is a lower bound for expected value of minus log of any arbitrary PDF. So Kullback-Leibler divergence theorem is defined for two distributions. We have two distinct distributions, fx of x and fy of y. So we want to calculate log of these two distributions. So ln of fx of x and ln of fy of x. So I put here x because I wanted to compare these two functions versus x. So now if I do averaging, because this guy is a function of x, this guy is also a function of x. So using this function of x, I could define a new random variable. So, and then calculate its expected value. So I define a random variable, let's say call this one z, which is equal to ln of fx of, instead of this guy, I put the random variable x, this will become, and let's say this is, let's say u is equal to ln of fy of x. Now, what we want to, this Kullback-Leibler divergence theorem says that is expected value of z over the distribution of fx of x. So if we average this z using the distribution of this guy is always bigger than or equal to the expected value of u or the same distribution of fx of x, because remember that distribution of y here is this PDF is used only as a function. Okay, so let's write the theorem and prove it. So in summary, we want to prove that expected value of log of a PDF, so this expectation is over this distribution, is always bigger than expected value of log of any other arbitrary distribution, but this expectation is also using this one. So other word, this is fx of x using this distribution. So the averaging is over this. That means that you get this function multiplied by this one and integrated. You get this function multiplied by this one and then you integrate it. So the value of the difference between this guy and this guy is called Kullback-Leibler divergence. So in other words, if I take log of fy of x, okay, and then if I multiply by fx of x and integrate it over different value of x from minus infinity to plus infinity dx, this function is maximized only and only if this distribution matches this distribution. So these criteria, these Kullback-Leibler divergence value, represent a matching of, sometimes this is data. So you could match or fit the data to a given distribution, or because sometimes you don't know the distribution. So this is a measure of the difference between two probability distributions from a true distribution f(x) of x to an arbitrary probability distribution. Now we'll prove this theorem. The proof is very easy. Often f(x) of x represent data or your observation or a piece of calculated probability distribution, and f(y) of y represent a conditional mode. So you could use these Kullback, and it is heavily used in machine learning as well, or in various applications. The proof is very easy, so we want to prove this one. Basically, this guy is an integral and this guy is another integral. Expressions are long, so we start with a very simple inequality, and the inequality is like that. So if you plot, let's say if you have a y, and if you plot log of y, so log of y at point y equal 1, it is 0, and asymptotically it goes to minus infinity here. So this log y at this point, if you plot the slope line, so you will see that this line of y equal y minus 1. Okay, so let's say if this axis is z, so z equal to y minus 1 is a line, and let's say this is z equal to log of y. So you see that this line is always above this logarithm. So we have this inequality, which we'll use it, and then automatically the proof is complete. So what I do, I know that the equality holds only for y equal 1. So if y equal 1, this equality is satisfied. Otherwise, the log value is smaller than y minus 1. So what I do in this equation, I put the ratio of the two distribution. So remember that here you have y, the distribution of y, and here you have the distribution of x. So if you substitute here and you take the logarithm of the ratio, you will get logarithm of difference, and then if you put y here, you get this one. So we have this expression. Okay, now I calculate the expected value of both sides, and the proof becomes evident. So I multiply both sides of this equation by f(x) of x. So the first term multiplied by f(x) of x, the second term is multiplied by f(x) of x. This one multiplied by f(x) of x is this one, and this one you get this one. Now if you integrate these from over value of x, integrate for x from minus infinity to plus infinity over all dx, and then you put on both sides of this inequality, so you get the proof of this. So so the integral of this one over x minus infinity to plus infinity is this term. Integral of this one is this one. Now obviously integral of this one from minus infinity to plus infinity is this one, which is equal to 1, because it is a valid PDF and total area of a PDF is equal to 1. And the same thing, the integral of this one is 1, and 1 minus 1 is 0. So this inequality obviously shows that this guy should be smaller than or equal to this one. So which is the statement of Kullback-Leibler theorem. Or alternatively, we could write that, because this this inequality is valid for all fx of x and all fy of y. So I could say that this is minus entropy. So this guy, the supremum value of this integral, if you maximize this integral over all, if you search over all possible PDFs, the one which maximizes this integral is the true PDF. So this is why this measure is used as a means to identify the distribution of a set of data. Obviously, there are other ways to do so.